So today we're diving into something pretty fascinating. Tiny machines that can actually levitate objects without touching them. In the world of microscale devices, that's a real game changer.
Absolutely. It's all about these Micro-electromechanical systems, or MEMS, that can hold and move tiny parts without any physical contact. And the device we're talking about today combines two levitation methods to control a small object in 3 dimensions, with some really clever features like adjustable stiffness and bistability.
Right, and that's huge because friction is a big problem when you're dealing with things at such a small scale. When parts rub against each other, they wear out fast and lose precision. So, contactless suspension, basically holding something in place without touching it, helps avoid all that.
Yeah, it's like, imagine trying to move a tiny ball on a sticky surface versus floating it on air. The floating option is way smoother and more reliable. In this case, they use forces like magnetic fields and electric fields to levitate and control the object.
Exactly. Now, this new hybrid device combines electromagnetic inductive levitation with electrostatic levitation. The inductive part uses tiny coils with alternating current to create magnetic fields that lift and stabilize a small aluminum disc, which they call the proof mass.
And then the electrostatic part uses electrodes to generate electric fields that fine-tune the disc's position and orientation. So you get precise control not just up and down, but also tilting and rotation.
The device itself is made of 2 main parts. One is the coil structure with these 3D microcoils that generate the magnetic fields. The other is the electrode structure with patterned electrodes that apply electrostatic forces. They're carefully aligned and bonded together.
The proof mass is about 2.8 millimeters in diameter, so roughly the size of a small button battery. The coils operate at a high frequency, around 9 megahertz, with currents between 100 and 130 milliamps. That lets them levitate the disc at heights from about 30 to 200 micrometers. To put that in perspective, that's roughly 1/3 to 2/3 the thickness of a human hair.
That's impressively tiny. And what's really cool is what this device can do. It can move the disc vertically with very fine control over that 30 to 200 micrometer range. It can tilt the disc about 2 horizontal axes by plus or minus 1 to 4 degrees.
Plus, it can rotate the disc around the vertical axis with an angular displacement up to 37 degrees at a frequency of 1.5 hertz. So it's not just holding it still, it can oscillate it in a controlled way.
Another key feature is adjustable stiffness. Think of stiffness like a trampoline. If it's stiff, it's hard to bounce on. If it's soft, it's easy. Here, stiffness means how much force you need to move the levitated disc. By changing voltages on the electrodes, they can make the suspension more or less springy during operation.
Right, and they showed that at a levitation height of 100 micrometers, they could double the angular stiffness. That means the disc resists tilting more strongly, which improves precision. It's like tuning the trampoline to be just right for the task.
And then there's bistability. That means the device can rest stably in 2 different states, either levitating or gently touching the silicon surface. It's kind of like a light switch that stays firmly on or off without flickering.
That's a neat feature because it can protect the device from damage in harsh conditions or extend the range of angular positioning. The device switches between these states by applying voltages beyond a certain threshold, known as the pull-in effect.
The experimental results are pretty solid. They demonstrated vertical positioning from 30 to 200 micrometers, angular tilting control from plus or minus 1 to 4 degrees, and angular oscillation of 37 degrees at 1.5 hertz.
Plus, they confirmed the doubling of angular stiffness at 100 micrometers levitation height and showed bistable operation with multiple stable angular positions. And importantly, their measurements matched well with theoretical models, which means they really understand how this thing works.
So what kind of applications do you see for this technology?
Well, nanoforce sensors come to mind. Devices that measure tiny forces with high precision. Also, digital micromirror devices used in projectors and displays, where tiny mirrors need precise control. And micro-actuators for tiny machines that require frictionless, precise movement.
It could also impact microgyroscopes and accelerometers, which are essential in navigation and motion sensing. The adjustable dynamics and bistability add a lot of versatility.
Overall, this hybrid contactless suspension is a significant step forward in MEMS technology. Combining electromagnetic and electrostatic levitation gives precise 3D control with adjustable behavior. and the bistable feature adds robustness.
Yeah, it really opens new possibilities for tiny machines that are more precise, adaptable, and durable. It's exciting to see how these advances at such a small scale can have big impacts.
Definitely. It's a great example of how combining different physical principles can lead to innovative solutions.
Well, that wraps up our look at this hybrid micro-machined contactless suspension. Thanks for exploring it with me.
Thanks. It was a pleasure. Looking forward to the next deep dive.